Hello, it's Stat 135, Lecture 28. You guys have a quiz 4 on Friday, November 16th, so we're postponing quiz 4 for 2 weeks. Last time we met the Mann-Whitney test, section 11.2.3, a non-parametric test for independent samples. Some notation: we denote the smaller sample size by x, the larger sample size by y. X is usually the control, y is usually the treatment group. We denote the smaller group sample x1 to xn, and the larger group y1 to ym. These are independent samples here. We have tx and ty being the rank sums of the two groups. Our null is that the distribution of xf is the same as the distribution of yg. The alternative is that they're not the same, so that's a two-sided test. If the null is true, then we would expect the rank sum for x not to be too extreme, not too small, not too large. And the reason that we look at tx is because that the critical value for that cutoff is in table 8 on page 821. But actually, the book mainly talks about another test statistic, ty, which is the rank sum for the y group, which is related to the rank sum of the x group by x. Tx plus ty is just the sum of all m plus n ranks. And the usual Mann-Whitney test statistic ty is so the usual Mann-Whitney test statistic is ty, but there's also another one called the Wilcoxon test statistic, which is uy, or also known as w in R, which is related to ty, as we'll see. Uy is the sum of all indicators where xi is less than yj, and this is approximately normal. Expected value mn over 2, because the total number of indicators is m times n, so you would expect, if the null is true, that half of the x's would be less than the y's. And uy and ty are related by this formula here that we derived last time, and the probability that your control is less than your treatment is a parameter called pi, which is approximated by uy over mn. So today what we're going to do is see all of this good stuff in R. I should mention that Wilcox.test is the go-to function. And if you're willing to assume that your distributions f and g are shifts of one another, so that introduces a parameter delta, then the Wilcox.test will provide a 95% CI for delta, and you can potentially do some power calculations. So we'll do an in-class exercise, and then we'll discuss the signed rank test, which is sort of the paired analog of the Mann-Whitney test. I also just want to note now that the t-test is the uniformly most powerful test. So remember that here I should write that delta is positive. So if your alternative is that mu x minus mu y is some positive delta, then we get this rejection region in blue here. And notice that this rejection region is all values of x bar minus y bar greater than z alpha times sigma square root of 2 over n, which has no sigma in it. So the rejection region is independent of sigma, so you get the same rejection region for every alternative where delta is positive. And so it's a uniformly most powerful test for delta greater than 0. Fantastic. So, and you can make a two-sided alternative version of this as well. But in any case, so that being said, the t-test, when applicable, when the assumptions of the t-test are made, you can't do better than that as far as power is concerned. And so that it will trump the Mann-Whitney test. But the Mann-Whitney test still is 95% as powerful, so that we won't be able to prove that result, but it's true. And but if the assumptions of the t-test are not satisfied, the results from your t-test can be meaningless, whereas the Mann-Whitney test will always be true because it's non-parametric and it doesn't matter what your distribution is. So we did this in-class exercise here. So notice there's some data cleaning here. Once we get to the non-parametric Mann-Whitney test, introduce mutate to introduce a new variable called rank, and summarize to introduce a new variable called sumRank. And we just go ahead and calculate the p-value by hand here. This is a two-sided p-value 0.0587. Now, if we just go ahead and use a t-test, then we'll see that we actually get a very close p-value, in this case 0.054, and so that lends credibility to the t-test, that the assumptions for the t-test are satisfied, even though this QQ plot looks rather suspect. And then we also do a Wilcoxon rank sum test, and we get a similar p-value here. So all are good in this case. So then we talked about a non-parametric Wilcoxon signed rank test, which is the analog for paired data. So let's, for example, a before-after study. So here we have, say, a before group and after group, a difference group DI here. So the null is that the distribution of DI is symmetric. So some will be positive, some will be negative. It's symmetric around 0. The alternative is that the DI is not symmetric around 0. And we can take the absolute value of the DIs and rank those, and then look at the signed rank by introducing the same sign that is the DI. And then our test statistic W plus is the sum of the positive signed ranks. And if the null is true, that the DIs are symmetric around 0, then this should be, so this should be, sorry, so this should be about the same as W minus. So in other words, W plus shouldn't be too extreme. So we need the sampling distribution of W plus. Note that there are 2 to the power n possible ways to assign signs to the ranks. So that's because if you look at the DIs, every DI could have a plus or minus sign attached to it. And if there are 4 rows, so there's 2 to the 4 different signs that we could have here. So in general, 2 to the n possible ways to assign signs to the ranks. So we have this theorem that the distribution of W plus is normal with mean n plus 1 over 4, and variance shown here. So we'll be using this, but I'll let you read the book proof in the book. I just want to show you actually how this is used in R. So here's a before-after study, and I just go and calculate. I calculate after some data cleaning. I do both a t-test. Notice that for t.test now you need to write paired equals true. And I also do a Wilcoxon signed rank test. So it's the same wilcox.test command, but make sure to write paired equals true. And you will get, in this case, a similar p-value indicating that the assumptions for the t-test were justified. We ended with an example that should help you in homework 8. So this is problem 11.6.26b. So except that I did a sort of a miniature version of that problem. So here I have one standard normal and two N1 ones. So let's say this is my treatment. So this problem is referring to independent samples. So this is Mann-Whitney test here. So determine the variance of the rank sum of the x's. Find the variance, in other words, find the variance of tx. Well, the variance of tx is the same as the variance of uy, since tx, because of the relationship of tx and uy, which you can look back and see what that is. So we're going to, right now, we're going to find the variance of uy, and uy is the sum of two indicators in this case, and these indicators are so these indicators are dependent on one another, as we'll talk about below. So there's a covariance term you need to compute, and so we go ahead and find that covariance term, but we see that along the way we need to figure out what the probability that x1 is less than y1 and x1 is less than y2. I don't know a closed formula way to do this, so I suggest you do a R code simulation, and I just give you the code here. You'll find that the probability that x1 is less than y1 and x1 is less than y2 is 0.634, and the covariance is then 0.056, and so then you can compute the variance of uy. So you're going to essentially do this for a general sample size n and m. So I lastly just want to remark that you may be surprised that the indicators are dependent, but the reason is that the bivariate normal distribution of x1 minus y1 and x1 minus y2 is an upward-facing football. It is they are correlated. These two random variables are correlated, and if, for example, it was, because basically both have x1 in it. If it was x1 minus y1 and x2 minus y2, then they would be uncorrelated. But here we have correlation. Okay, so I wish you guys all a happy weekend, and I'll see you next week.